All right. Now we have seen differential equations. So, but since they are, equations, so it means that we should be able to solve them, right? So, and the kind of the first question that you probably have is, what is a solution to a differential equation, right? And basically, differential equation has an unknown function, right? So, and if this is an unknown function of x, right? So if y of x is an unknown function, so a solution of a differential equation is a function such that if you substitute it into the equation as y, then basically the equation becomes a correct equality. So here is an example, right? So here we're supposed to verify that the given function is a solution to the given differential equation, right? So how do we do that? Now, we are given the formula for theta of t, right? So what is going to be theta prime of t? So the first derivative of the given function is going to be, okay, so the derivative of sine is cosine, right? So it's going to be 3 times, well, omega. This is omega times cosine of omega t. The derivative of a cosine is minus sine, so it's going to be minus pi omega times sine of omega. Okay, so the next thing we need to compute, since our differential equation has order 2, it means that we've got to compute the derivative uh, of this known function for up to order 2. So theta double prime is going to be, so now I've got to differentiate theta prime, right? So differentiating theta prime, I'm going to get, the first term is going to be, well, the derivative of cosine is minus sine, so it's going to be minus 3 times omega squared sine omega t minus the derivative of sine is cosine, so minus pi omega square cosine of omega t, right? Well, so we can take out omega square just to simplify, so it's going to be and probably the minus omega square, so it's going to be minus omega square times 3 sine omega t um, plus pi cosine of omega t. Okay, so this is theta double prime. So what is now theta double prime plus omega square theta? Well, basically I've just written down theta double prime. So what I need to do, so let me just add plus omega square times my theta, and here is my theta, so I just need to copy it down. So 3 sine omega t plus pi cosine omega t. Right, but notice that um, I have this term and this term. They look exactly the same, only the only difference is that there is a negative sign here and a positive sign here. So it means that they just cancel each other out, and I get 0, right? So, and the differential equation precisely tells me that that theta double prime plus omega square theta is 0. And I have verified that if I replace theta with the given function and compute its second derivative, and then I just compute the expression theta double prime plus omega square theta and simplify it, I will in fact get 0, right? So it precisely means that this given function is a solution of the differential equation. Now, so here is the same thing printed. Now, differential equations have infinitely many solutions. Now, why is that? So let me give you an example. Well, this is something familiar to you from I don't know, from junior college, from poly, maybe even from secondary school. You know that when you integrate, say, some function like, I don't know, x dx, right? So what you get is x squared over 2 plus c, right? So there is this plus constant. Well, but when you integrate, what do you do? So when you are integrating some function, you are looking for another function whose derivative is the given function, right? So it means that if you denote this by y, it means that you are actually looking for a function y such that dy dx equals x. But this is, in fact, just a differential equation, right? I mean, it is probably a simple differential equation, but apparently it is a differential equation. And so what it means is that integration familiar, from secondary school is in fact a particular case of a differential equation. So it is a differential equation where the right hand side of my differential equation, or just does not have the dependent variable. It only has the independent variable. Well, but at the same time, the solution to this differential equation is x squared over 2 plus c, right? And this formula, it describes all possible answers to this differential equation, not just a particular one. So it tells me how to obtain all possible solutions. So because it tells me that x squared over 2 is a solution, that x squared over 2 plus 2022 is another solution. So x squared over 2 minus square root of pi is yet another solution, and so on and so forth, right? So if you replace c with any particular number, you will get a solution of the differential equation, right? And this is called a general solution. Well, and the general solution to any differential equation is going to have something like plus c. Well, if your equation is a first order differential equation, it's going to have plus constant, or maybe it doesn't have to be plus constant. We will see that it is not necessarily plus c, so it can be something like c times something else. So, but there will be an arbitrary constant in the general solution of a first order differential equation. But then just applying kind of the same kind of logic, if you have a second order differential equation, it's going to involve like integration two times. So which means that the general solution is going to have two different constants, and a third order differential equation, is going to involve three constants and so on, right? So here is an example. So this function c1 sine omega t plus c2 cosine omega t is a general solution to this differential equation. So here omega is any particular fixed number. So, well, yeah, so omega, you can think of omega as something like, I don't know. So imagine that omega is square root of 2022 or something, right? So then this formula, c1 times sine of square root of 2022 t plus c2 cosine square root of 2022 t. It describes all possible solutions to the differential equation theta double prime plus 2022 theta is 0. All right, to solve a differential equation, so the verb to solve here means to find the general solution, so which in turn means to find all possible solutions. That there are different types of differential equations. Well, to be frank, most of useful differential equations in practice cannot be solved explicitly. Some can, right? But very often they cannot. So if you cannot solve a differential equation in closed form, then there are some other tools in mathematics that will still help you to work with differential equations. But in our course, we are just going to look at a few types of differential equations that can be relatively easily solved in closed form. So there are separable differential equations and linear differential equations. We're going to learn them today, and in the remaining two lectures, we're going to look at homogeneous equations, Bernoulli equations, exact equations, and second order linear differential equations with constant coefficients.